I want to continue my discussion on how to evaluate limits algebraically. In the first video, we saw one technique, factoring. All right, if we can factor our original function so that we cancel the term or divide out the term that's basically causing the discontinuity at that point, then we can transform our function into one that is continuous at the point that we're trying to find the limit. So I gave I'll just quickly repeat it. Limit is x approaches 2 of x squared minus 4 over x minus 2. Well, this equals x minus 2 times x plus 2 over x minus 2. So those cancel or divide out. I mean, x minus 2 divided by x minus 2 is 1 for all values of x. So then we're left with the limit. This is equivalent to the limit as x approaches 2 of x plus 2. But since this is continuous at 2, then we can just put in 2 for x. So that's 2 plus 2, and that equals 4. All right, so let's see another example. Let's take a look at just do a different technique in a different color to keep it separate. Let's take a look at the limit as h goes to 0 of 3 plus h squared minus 9 over h. So the first thing, I should have mentioned this in the first video, but in order to use these techniques, what we basically need is an indeterminate form. Notice here, if I put in, or at least the indeterminate form is a good sign that an algebraic technique could work. If I put in 2 here, I get 0. If I put in 2 in the denominator, I get 0. I get this 0 over 0. So let's see what happens if I put in 0 for h here. Well, I get 3 plus 0 squared minus 9 over 0. Well, that's 3 squared that's 9 minus 9 over 0, which is 0 over 0, so this is an indeterminate form. But we have this term 3 plus h that we could square this out, and maybe something good will happen if we do that. So let's try that. If we have, it's 3 plus h squared, so it's 3 plus h times 3 plus h. So you can FOIL it. There's other ways, but so that's 3 times 3 is 9, and then the outer, that gives me 3 plus h, and the inner gives me, 3h, and the inner gives me 3h, so I have 6h, and then h times h is h squared. All right, so if I expand that out, this is what I get. So now let me say I'm going to take the limit as h goes to 0 of 9 plus 6h plus h squared minus 9 over h. All right, so 9 minus 9 is 0. That leaves me with 6h plus h squared over h. Now notice now the numerator has a common factor of h. So let me factor that out. I can take out an h, and I'm left with 6 plus h over h. All right, now h divided by h is 1. So now I'm left with the limit as h goes to 0 of 6 plus h. All right, so whereas this original function is discontinuous and indeterminate at h equals 0, this is just an algebraic technique of expanding. So that's our second one. We can expand. If there's something that could be expanded, try it, see what happens. If you have an indeterminate form, it's likely to be a useful technique to try. So this is algebraically equivalent to this. In other words, their limits are the same at that point. But this one is continuous at h equals 0. So we can use this continuity. This is kind of a shortcut now. We'll just substitute 0 for h. So that gives me 6. And you could verify this if you looked at this if you looked at a graph of this or examined the values of this function near h equals 0, you would find that they are indeed approaching 6. All right, let's try another one. Let me give you this function. Let's take the limit as t goes to 0 of the square root of t squared plus 9 minus 3 over t squared. All right. Well, there's not really anything we can simplify here. This doesn't really factor, right? A difference of squares factors, but a sum of squares doesn't. We can't really take a t or a t squared out of the numerator because I only have a t squared over here, and even that wouldn't, I'd have to have a t in both of these terms, and then it would have to be a perfect square to take it outside of the square root. I also don't have a t over here, so the two techniques we've looked at so far, factoring and expanding, don't seem like they can help us here. So here is a little trick. It is called multiplying by the conjugate. And so, for example, this we have the square root of something minus 3. The conjugate of that is the square root of the same thing plus 3. Okay? So this is the conjugate. The difference here is right here. All right? That's what defines the conjugate. All right? And we'll see why we want to do that in just a moment. But this is the conjugate of that, and we want to multiply it. But we can't just multiply it by that. We have to multiply by something that's equivalent to 1. Otherwise, we've actually changed the function into something else. So we multiply by square root of t squared plus 9 plus 3 over the same thing. Square root of t squared plus 9 plus 3. Okay, now we're going to see why multiplying by the conjugate is helpful. The main idea here is that when I take a square root times a square root, basically I'm squaring the square root, so the square root goes away, right? The square root squared just gives you back whatever you started with, right? So so square root of t squared plus 9 times the square root of t squared plus 9 is just t squared plus 9, all right? Now, the reason we multiply by the conjugate, notice that the outside is going to be 3 times the square root of t squared plus 9, positive, and the inner term, so for foiling, first, outer, inner, and then last. The outer and the inner are going to be the same expression, 3 times square root of t squared plus 9, except this one will be positive and this one will be negative. So they cancel, all right? Or one minus the other is just 0. I don't really have room to write it over here, but I think you could see that. Go ahead and in your own notes try to write that out if you're not seeing that. So the outer and the inner terms cancel, and then I have minus 3 times plus 3, so that's minus 9. Now another trick to making this technique work is when we multiply the denominator, don't simplify. Just write t squared and keep in parentheses here the t squared plus 9 plus 3. Because notice one of the issues here, actually I guess we should have checked that this is indeterminate, right? But one of the issues here is that this t squared in the denominator, if I put in 0 for t, I'm dividing by 0. That's undefined. Now notice if I had put 0 in, let's just go ahead and check to see that this is indeterminate. I would get 0 plus 9, square root of 9. So 0 plus 9 is 9, square root of 9 is 3, 3 minus 3 is 0 over 0. So indeed I would get 0 over 0 if I put in 0 for t. Okay, we've multiplied by the conjugate, and because this is a complicated expression for 1, we have something that is algebraically equivalent to our original. This was our original function. All right, let's simplify here a little bit and see what happens. So the 9 minus 9 is 0, so I'm left with t squared over t squared times square root of t squared plus 9, that's all under the square root, plus 3. This is why we don't want to expand that t squared, because we could have distributed the t squared to this term and to this term. But by leaving it out, we can see that I have a t squared term in the numerator denominator. Divide that, I'm left with 1. Some students want to call that 0, but if I take anything and divide by itself, I get 1 over the square root of t squared plus 9 plus 3. Okay, so this function here is algebraically equivalent to this function here, and this one happens to be continuous at t equals 0. Notice now, so because they're algebraically equivalent, the limit of t as t approaches 0 of this is the same as the limit as t approaches 0 of this. But this, because it's continuous, we can evaluate the limit by substitution, by substituting in 0 for t. So let's go ahead and do that. I get the square root of 0 squared plus 9 plus 3. Well, this expression here, that's 9 square root, so that's just 3, and 3 plus 3 is 6, so I get 1/6. All right, so again, we could verify graphically, numerically, that as we get really close to 0, this original function seems to get closer and closer to 1/6. But by using continuity, we were able to verify it more rigorously, because we know that these two functions are algebraically equivalent. This one's continuous, so we can evaluate this limit by substitution. Okay, so let me just add that to our list. We have this idea of multiplying by the conjugate. So the clue there that you'll see is the square root. All right? When you have a square root, then you might want to be thinking about that. That's a good time to think about multiplying by the conjugate. Okay, let's see another example. Different color. Let's try the limit as x approaches, let's say, yeah, let's do that. Limit as x approaches 9. We're having a lot of 9s and 3s in our examples, but that's okay. These are just examples. Square root of x minus 3. So the first thing is to see whether or not this is indeterminate, right? So if I put in 9, I get 9 minus 9 over the square root of 9 minus 3. That's 0. Square root of 9 is 3 minus 3. That's 0. So it is indeed indeterminate. The square root, like I said, that's generally, if you see the square root, that's a good time to think about multiplying by the conjugate. In this case, the square root's in the denominator. All right, so let's try that. So x minus 9 over the square root of x minus 3. So the conjugate, we want to multiply by the conjugate over itself, right? Because this has to be equivalent to 1. So the conjugate is square root of x plus 3, and I need to put that in the numerator and denominator. All right? Okay, now I'm going to multiply through. So again, so here I'm going to have some simplification when I'm multiplying these square roots. So notice up here the square root is numerator, so that's where the simplification occurred. That's going to happen down here. So up here I just want to write these. I don't want to mix them up. I don't want to FOIL them and get it all kind of distribute and get everything all mixed together. I want to keep them separate because I'm expecting one of these terms to show up in the denominator, so I can divide it out and then get something that's continuous at x equals 9. So down here, let's go ahead and, since I couldn't do it all up here, let's go ahead and completely expand this out so you can see. Square root of x times the square root of x is x. The outer term, 3 times the square root of x, is 3 times the square root of x, minus 3 times the square root of x, minus 3 times 3, right? Minus 3 times positive 3, that's minus 9. So this is what always happens when you multiply by the conjugate. The outer and inner terms become 0, all right? So what I'm left with is just x minus 9. This is the whole motivation for multiplying by the conjugate. So we cancel. I'm left with the square root of x plus 3. Now I know the limit of that as x approaches 9 is the same as the limit of this as x approaches 9 because they're algebraically equivalent. Difference is this one is continuous at x equals 9, so I can just substitute, right? So I can just put in 9 for x. Square root of 9 is 3 plus 3 is 6. I do want to point out that there's another way to approach this, though. You can think of x minus 9 as a perfect square, right? Because x is the square root of x squared, right? So in other words, if I were to write this, let me just do it down here. If I were to write that as the square root of x squared minus 9 over the square root of x minus 3. Because I'm just rewriting x as the square root of x squared, right? We all agree that those are the same. Now, a difference of squares factors, so this is a perfect square now, and this is as well. Its square root is 3, so I could factor this into the square root of x plus 3 times the square root of x minus 3 over the square root of x minus 3. All right, so divide those. I'm left with the square root of x plus 3. I know this limit is equivalent to the original one, and I get the same answer that I did up here because this is actually the same function. So in this case, two different techniques were possible. I could multiply by the conjugate, or I could factor. Those are two that we already know. All right, so factoring worked. If I think of this as a perfect square, I can factor it. Otherwise, I can always multiply by the conjugate. Okay, just a couple more examples. All right, let's take a look at something like the limit as x approaches pi over 2 of tangent of x over secant of x. Yes, trig function. Everybody loves the trig functions. So we all remember that tangent is undefined at pi over 2, and so is secant. So this gives me basically undefined, not 0, but actually gives me undefined over undefined, which is another indeterminate form. All right? But these, we remember, now I know you already remember the tangent of pi over 2 is undefined. And you also know that the tangent of x is equivalent to sine of x over cosine of x, right? And what's cosine of pi over 2? It's 0. That's why this one is undefined. And we also remember that secant of x is 1 over cosine of x. And again, because cosine of pi over 2 is 0, this is also undefined. But these, so here's another technique, which is basically to just rewrite these trig functions in terms of things that they're equivalent to, and see if we can do some simplification here. All right. So what I'm going to do is rewrite this as limit as x goes to pi over 2. I'm going to rewrite this as sine of x over cosine of x. That's the numerator, all over 1 over cosine of x. All right. Now, if I divide by a fraction, I multiply by its reciprocal. So I'm going. This is equivalent to. I should say not multiplied. This is equivalent to sine of x times cosine of x times the reciprocal, cosine of x over 1. So those divide to give us 1, and I get sine of x over 1, which is just sine of x. All right. Now again, this original function is algebraically equivalent to this one. So I know that this limit, the limit of this function, is the same as the limit of this function. This function, sine of x, is continuous at x equals pi over 2. So I can just substitute sine of pi over 2, which is 1. All right? So I don't really have a name for this one. But I don't know, we could just say substitute equivalent functions or something along those lines. This might be particularly useful. And what I mean by equivalent functions is, you know, tangent can be rewritten as sine over cosine, secant can be rewritten 1 over cosine. So using kind of the definitions of these trig functions, we could rewrite this and transform it into a function that has the same limit and is continuous at x equals pi over 2. Okay, I have one more example here. So let's take a look at the limit as x approaches 1 of 1 over x minus 1 over 2 over x squared minus 1, this whole thing. All right, so if I just put in 1 here, I get 1 over 0 minus 2 over 0. All right, so I get basically undefined minus undefined, right? So here I had undefined divided by undefined. So this is also an indeterminate form. But we can see immediately here, it looks promising maybe that we could rewrite this as a single expression rather than the difference of two, and maybe some good things will happen. So the first thing to recognize is that this is the same as, because this is difference of squares, this is x plus 1 times x minus 1. So let's first write 1 over x minus 1 minus 2 over x minus 1 times x plus 1. And what we need is a common denominator. So notice, if I were to multiply this term by x plus 1 over x plus 1, I would actually have a common denominator, right? The denominator here would be the same as this, and then I could combine the numerators. So let's go ahead and do that. So this is going to be x plus 1, that's my contribution for this side, and then minus 2 over, and our new common denominator is x minus 1 times x plus 1. All right, now the numerator simplifies, right? X plus 1 minus 2 is x minus 1 over x minus 1 times x plus 1. All right, so that I can divide. I'm left with 1 in the numerator, so I'm left with 1 over x plus 1. And I know the limit of this function here is the same as the limit of the original function, because basically I just took these two terms and combined them into a single term using a common denominator. So since I've used this algebraic technique, I know these limits are the same. This one is actually continuous at x equals 1, so I can evaluate this limit by substitution. So this is the same as using the continuity, 1 over 1 plus 1, which is 1/2. So I'll just call this technique combining terms. You know, if we have two different terms like this that lead to undefined minus undefined, or maybe undefined plus undefined, or something like that, if we combine terms, often this will include finding a common denominator, then many times it will lead to a simplification to a function that's algebraically equivalent and has and it's continuous at that point. So we can use that continuity to evaluate the limit. All right, so here's just a quick review of our list of different techniques. I do want to mention real quick before I finish here that this doesn't always work. Let me just give you one example. Sine of x over x. So if we take the limit of that as x goes to 0, we get an indeterminate form. But there is not really anything algebraically that we can do to transform this function into one that's continuous at 0 and use the continuity to evaluate the limit. So I want to just point that out. Just because you have an indeterminate form doesn't mean one of these will necessarily work. As a matter of fact, we will talk about this in the lecture about finding trig limits in terms of we've already kind of looked at this and seen that the limit appears to, if we look at the graph and we look at the table of numbers, the limit appears to be 1. But how to kind of get at that more rigorously so that we can be sure that it's 1, algebraic technique won't work. So if you have an indeterminate form, try an algebraic technique, but I don't want you to think that every time you have an indeterminate form, it's always going to work.